Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're shifting gears and we're leaving behind the heterolytic cleavage reactions of SN1, SN2, E1, and E2. We're going to look at homolytic cleavage and consider free radical reactions. First, we're going to take a look at monohalogenation. Now, free radicals are atoms, molecules, or ions that possess one or more unpaired electrons. These represent just a few examples. If you take H2 gas and you split the bond between the two hydrogens homolytically, such that one electron goes with each hydrogen, and you get a neutral hydrogen atom, that is a proton with one electron, you have an unpaired electron. Hence, this is a hydrogen radical. The X here can be either a chlorine, bromine, or iodine, or even a fluorine. Any halogen can be split. They exist as dihalogens, F2, Cl2, Br2, I2, and if you split them homolytically, you get halogen with 3 lone pairs and a lone electron, a radical. If you take ethane and split its sigma bond, so you get 2 methyl dots, you will have a methyl radical. Even oxygen exists as a diradical. It turns out, and we're going to see this sooner, we're going to actually come and have a closer look at this. Oxygen's Lewis structure, drawn like this, is not a correct representation. It's the only acceptable Lewis structure, I'll grant you that. However, if we do molecular orbital description of oxygen, we learn that oxygen is a diradical and exists with 2 unpaired electrons. Now, what we want to do is examine monohalogenation of alkanes utilizing a free radical process. This is often referred to as the chain reaction mechanism for free radical reactions. Now, a chain reaction mechanism always begins with what is referred to as an initiation step. So, chain reaction mechanism. And the first step, initiation, involves the formation of the radical itself. So if you like, step 1 is initiation. Initiation. Now, if, for example, I have Cl2, chlorine consists of lone pairs and a single bond to another chlorine, so Cl2 gas. And chlorine can readily have its single bond broken. This can be done using light. We symbolize light as H nu. Ultraviolet light often is used. Or we could use heat. Applying either light or heat, you can split that single bond homolytically. That is, one electron of the 2 electrons in the bond goes to each atom. And so you get 2 chlorines that have its lone pairs plus a dot. You get 2 chlorine dots. The next step is that this radical can attack alkane that is present. This step in the chain reaction mechanism is known as the propagation steps, and there's often more than one step connected to it. So let's take a look at the propagation steps. So step 2, propagation steps. I probably should unplug my phone so we don't get interrupted. Propagation. So our propagation steps. As I said, we have chlorine radical. So here's my lone pairs around my chlorine, and it's a dot. And let's use the simplest alkane, methane, and focus on one carbon-hydrogen bond. So I will draw my methane thusly. Our simplest hydrocarbon, methane. The Cl dot can abstract a hydrogen. One electron will combine with the electron. That will leave one electron on the methyl. Hence, we will produce HCl with its lone pairs, and we will have a methyl dot. Now, methyl radicals are extremely reactive. You shouldn't think that the concentration is very high of the radical in solution. In actual fact, it's quite low, but they are extremely reactive. Right? Now, note the methyl dot can react with the large amount of compound that's present. Now, you say, well, hold it. There are two compounds present in larger quantities. That's the Cl2, from which in the initiation step, and the methane. And you'd be correct if you assume that the methyl dot attacks the Cl2. And the Cl-Cl bond of a Cl2 breaks. One electron goes towards the methyl dot, and one electron stays with the chlorine, and we get methyl chloride. Plus, now we have Cl dot. Now the Cl dot can go back to the original step 1. Let's call this equation 1 and equation 2. So chlorine dot from equation 2 goes back to chlorine dot in equation 1 and attacks another methane. If I add up these reactions in the propagation step, the Cl dot on each side of the equation will cancel. The methyl dots on each side of the equation cancels. And what I end up with is Cl2 plus CH4 goes to HCl plus methyl chloride. Now, you might immediately think, well, hold on a second. Why did you have your methyl dot attack a Cl2? For that matter, why did a Cl dot attack a methane? Couldn't a Cl dot attack a chlorine? Couldn't a Cl dot react with a chlorine? Yes, but that gets you nowhere. Yes, there will be molecular collisions between Cl dot and chlorine. If that happens, notice a chlorine dot will abstract a chlorine and make Cl2, and you just get another Cl dot. You get nowhere. Also, if a methyl dot attacked a methane, look what you get. You get a methane and a methyl dot. So in either case, even though these molecular collisions may occur, they do not change the reagents at all. Only the reactions between Cl dot and methane produce a change, generating a methyl dot. And methyl dot with Cl2 produce a Cl dot that allows the reaction to proceed. These reactions just regenerate your reagents, and hence they're not included because they produce no change to the system. Okay. Now, one of the interesting things to note is there's potentially a complication to this if you do this reaction in air. Oxygen can interfere with the reaction, producing less reactive peroxide radicals. Remember, oxygen is a diradical. And if there's lots of it dissolved in solution, in other words, you're doing the whole reaction in a standard air atmosphere, the methyl dot, before it hits a chlorine, might hit an O2 molecule and link up. And if it does, you get a peroxide. Peroxides are less reactive, and the peroxide radical can lead to some suppression or what is referred to as quenching of the reaction. Okay. Now, what we want to do next is take a quick look at the termination step, but I don't want to rub off the first reaction, so I'm going to take the time to clear the bottom half of the screen, erase it if I can. And we want to keep the propagation steps up because they're going to be important to side reactions. But before we get to side reactions, let's take a look at how the actual chain reaction stops, because it looks like it would go on forever. Well, the obvious answer is that the chain reaction propagation steps is dependent on the presence of radical. You have radical propagation step happen. If radicals disappear, this reaction stops. Now, because radical concentration is so low, usual molecular collision is with either the methane or the chlorine. But if two radicals happen to collide and couple, you will terminate your propagation steps because there will be no more radical present. So you can quench the reaction by losing your radicals, and you can lose radicals through what are called termination steps. What do I mean, termination steps? Well, although the probability is much lower that this would happen, it does occur rarely. And because of that, two chlorine radicals can come together, crash together, and produce Cl2. So unless you're regenerating more chlorine radical, you could terminate the reaction by removing chlorine radical. Likewise, a chlorine radical could crash into a methyl radical. If that happens, you would produce chloromethane. Lastly, two methyl radicals can react and produce an ethane. Okay. So there are a variety of termination steps, and in these termination steps, as you get larger alkanes, you can introduce what are known as disproportionation, which are oxidation reduction steps as well. Now, there is a major problem with the chain reaction mechanism in the propagation steps that can make it not as synthetically useful as other reactions unless you're very, very careful. And those are side reactions. And we want to take a look at some of the side reactions that can occur. And think about what happens as a reaction progresses. Initially, we have large amounts of methane and chlorine. The chlorine is split with ultraviolet light, producing tiny amounts of chlorine radical, and the reaction starts. You get HCl methyl dot, and you start producing methyl chloride. Initially in the reaction, the concentration of methyl chloride is extremely low. So molecular collision is favored between chlorine radical and methane, and CH3 dot and chlorine. But as the reaction progresses, if you're using stoichiometric quantities, the concentration of methyl chloride begins to rise. Eventually, it begins to exceed the amount of methane. Molecular collision now starts to become favored with the methyl chloride rather than the methane. Instead of colliding with methane, the chlorine radical collides with the methyl chloride. If that happens, you get HCl again, yes. But this time you get a CH2Cl radical, a methylene chloride radical. Now the methylene chloride radical, Cl, CH2 dot, can react with Cl2. If it grabs an electron from the bond between the Cl2, what do you get? You get CH2. You get methylene dichloride or dichloromethane and Cl dot. We're going to call this a side reaction. Okay. Side reactions. And if we add this up, what's the overall reaction? Well, the chlorine dot cancels with the chlorine dot. The methylene chloride dot cancels with the methylene chloride dot. And overall, we've got Cl2 plus chloromethane goes to HCl plus CH2Cl2. So we see if chloromethane was our target molecule, or methyl chloride, as the stoichiometry shifts and product begins to predominate over the methane, the product starts getting attacked and you start producing quantities of dichloromethane. Now this side reaction can continue and eventually the chloromethane can start dropping and you can start getting large amounts of methylene chloride. That means chlorine radical would attach the CH2Cl2. Now I'm not going to draw both steps of the propagation steps again for the next side reactions. I'm going to just write the summary reaction. But Cl2 could begin attacking CH2Cl2. You would just change the propagation steps as necessary. And if it abstracted hydrogen, it would make HCl, and you'd have chloroform, CHCl3. And finally, as the chloroform concentration built up and it began to get attacked, Cl2 would react with chloroform, and you'd get carbon tetrachloride in HCl. Wow. So these are all side reactions that compete with the desired reaction of preparing methyl chloride. And these will give you a large mixture of different chloromethane derivatives. Now, you can favor a reaction one over the other. For example, if I wanted chloromethane as my product, what could I do to minimize these three side reactions? Well, the reason these side reactions happen is because the concentration of methyl chloride rises high enough to compete with methane. If I prevent that from happening, then I wouldn't get the side reactions. How can I prevent that? Use a large excess of methane. Suppose I use hundreds of thousands of moles of methane versus only a few moles of chlorine gas. The Cl dot, few moles, would only produce a few moles of methyl chloride, and there'd still be a huge excess of methane left over. That means the probability of molecular collision between Cl dot and the product is low compared to Cl dot with methane. So you'd only get tiny amounts of the impurities. So use a large excess of methane, okay, a large excess of CH4 to produce methyl chloride. What if you wanted carbon tetrachloride as your product? Then use a large excess of Cl2. If you think about what's going to happen in that scenario, the Cl2, there'll be so much Cl2 you'll completely chlorinate methane to get methyl chloride. And then there's so much chlorine around, methyl chloride can be attacked to give you dichloromethane. Dichloromethane can be attacked to give you chloroform. And chloroform can be attacked to give you carbon tetrachloride. You can vary concentrations to favor or optimize or produce a major product. And if there is an industrial market for all 4 chloromethanes, you could fractionate them and separate them based on boiling point. Okay. Let's talk about the relative reactivities now of the different halogens. Relative reactivities of the different halogens. In terms of relative rates, F2 gas reacts much faster than Cl2, which reacts faster than Br2, which reacts faster than I2. If you attempt to do the halogenation, for example, of methane. This is not due to the ease of cleavage of the X2 bond. That is, it's not the bond dissociation energy. F2 has a greater bond dissociation energy than I2. All right? The BDE, this is rate for halogenation. Yeah. Run out of room. Monohalogenation, whereas this is BDE, bond dissociation energy. What's that mean? Remember, bond dissociation energy is the amount of energy you have to put to break the F2 bond. If it takes more energy to break the F2 bond, you would think the reaction would be slower, but F2 reacts faster. So simple bond dissociation energies can't be used to explain this rate. The order of reactivity may actually explain in terms of the relative enthalpies, the delta H's of the reactions, and the related energy of activations that occur. Let's take a look at X dot. I'm going to write it as X dot here so I can put down any halogen I want. And we're going to start with X dot reacting with methane. So here's methane. And we're going to produce HX. And we're going to get methyl dot. And we're going to report a delta H here. I'm right up here, delta H. Our delta H that we're going to report is in kilocals per mole, so I'm going to put per kilocals per mole. Oops, forgot the C. Kilocals per mole, or if you like, kilocals mole minus 1, whichever you like. So all the numbers are right here in kilocals per mole. And this is an exothermic reaction. It's minus 31. Now the CH3 dot, as I said previously, and remember X here is fluorine. So I should write that down, and I will. X reacts with fluorine 2. Gives me H3X plus X dot. The second step, the delta H is also exothermic, minus 71. And if we add this up, the X dots cancel, the methyl dots cancel, and we get CH4 plus X2 going to CH3X plus HX okay. And we have 100. We had negative 102 kilocals per mole. This is for X equals fluorine. What do you get if you draw the potential energy diagram when the X is exothermic? Well, it turns out that in general exothermic reactions, the energy of activations tend to be quite small. So we start out here with F dot and CH4. I'm going to put F dot plus CH4. And we go over a hump for an energy of activation, and it's exothermic, so we drop to a lower place. And remember, this is the product, HF plus CH3 dot. And then the CH3 dot can attack F2, and when it does so, goes through another energy of activation, and there's a big drop in energy, and we get CH3F plus F dot. So this represents potential energy. And this is time or progress of reaction. I'll just write time here. Often we call it progress of reaction. Okay. Notice, now let's change color. If I split the line here, this is, if I label these reactions 1 and 2, this is the energy of activation 1. And this right here, of course, is my delta H for 1. This is my delta H, and as we see, it was exothermic at minus 31. And we can do that again for the next step. Because the reaction's exothermic, the energy of activations are often small. This is energy activation 2. Exothermic reactions typically have smaller energy of activations than endothermic reactions. And here, delta H equals minus 71. So, we can draw a potential energy diagram. So why is F2 reactive, more reactive? You have small energy of activations, you have a large amount of heat energy being released. That heat energy can be absorbed by the reactants to overcome the energy of activations, and the reaction progresses faster and faster and faster. F2 reactions, because of this, are typically explosive. And as such, halogenation reactions with F2 are usually avoided. They are extremely dangerous because the amount of heat energy given off can allow the reaction to get out of control. The only way to safely run an F2 reaction is to use a noble gas such as helium or neon, noble gas that F2 will not react with, and to dilute the F2. So that the reaction is slowed down. You reduce the probability of collision and try to keep the system cool and try to keep the reaction under control, but it's extremely dangerous. Okay, let's check the other extreme. So that was F2. What about I2, the slowest one to react? Why is it so slow? Well, we're going to change. The propagation steps remained exactly the same. Okay. Propagation steps remain exactly the same. However, the enthalpies change. Okay. So we're going to erase this and take a look, if we can. Take a look at what happens in the case of iodine. X is I. Well, it turns out that the first reaction is quite endothermic, plus 33. The second reaction is exothermic, but it's only minus 20. So overall, the reaction is endothermic at plus 13 kilocalories per mole. If you translate this into the potential energy diagram, you have I dot and CH4, and it reacts to produce HI and CH3 dot. HI and CH3 dot. The CH3 dot then can react with I2, and if it does so, now we get a bit of an exothermic reaction. Not quite as low as the original. And you get CH3I plus I dot. If we label this as we did before, you notice some things result because of the endothermic step. You notice, for example, a large energy of activation 1. The first energy activation is very large. The delta H, right here, which is plus 33. So that's your delta H. Your second, because of the reaction being exothermic, the next energy of activation is quite small. And although that step is exothermic, overall you see there is a small energy gap here. All right. So the I2 reaction, being endothermic, does not produce sufficient energy to sustain the rupturing of the I2 bond. Overall, I2 reacts too slowly to efficiently produce alkyl iodides by this method. F2, far too reactive, can cause explosive reactions. I2, too slow. Cl2 and Br2 are intermediate in reactivity. They lie somewhere between the two extremes. Because of this, they possess reaction rates that are satisfactory for the synthesis of alkyl chlorides and bromides. F2 can only be used in noble gas atmospheres. We must dilute the F2 gas to slow the reaction down and prevent an explosion. All right. What about the radical itself? In reaction mechanisms previously SN1, SN2, even E1, E2, we are concerned about stereochemical changes. if we're going through a radical, such as this structure, we must understand the geometric changes that take place because of the formation of a radical. We must not only understand the geometric changes, but in order to understand and obtain those, we must understand the structural features of the radical itself. So, let's consider some of the geometric implications of these reaction mechanisms, or, yes, a terrible word once again, stereochemistry. Ooh, nasty. Stereochemistry. You never get away from it. Whenever you're going to look at mechanism, you're always concerned about stereochemical changes in the molecule. Stereochemistry. Well, what about the structure of the radical itself? A free radical carbon in alkyl radicals is sp² hybridized. You can't really determine that from hybrid orbital number because remember you count lone pairs and you count atoms. What do you count for a lone electron? Well, that doesn't fit our hybrid orbital number calcs, but suffice to say, the radical is sp² hybridized. That means the dot lies in a 2p orbital. I'm just going to say empty because I'm so used to talking about carbocations. And what we have here is bond angles of 120 degrees and carbon's sp². Okay, so carbon is sp². And the radical is in a 2p orbital. So this is my 2p orbital. So, well, we've seen this before, this kind of shape in carbocations. What happened in the SN1 reaction mechanism when you did nucleophilic attack on a carbocation? Do you remember? What happened to stereochemistry? That's right. Your nucleophile could attack either site equally. There was a 50-50 chance of coming in either above or below. If you came in above, you would get a substituent that looked like this. And if these R groups were all different, you'd get R, R, R. If you attack from underneath, you'd get this, R, R, R. And if all the groups are different, you'd get a mirror plane. They'd be a pair of enantiomers. You'd get a racemic mixture. And indeed, the evidence for this stereochemistry of the radical, the fact that it's trigonal planar, is the fact that you get such racemization. So if you started with an enantiomerically pure alkane, where you had an H here and 3 different R groups, and then you pulled off the H to make a radical, and then you did the radical coupling, your pure enantiomer would give you a racemic mixture. Okay, so stereochemistry leads to racemates in radical reactions. All right. What about stability? Radical reactivity and stability. Well, in order to understand radical relative reactivity, we've got 2 steps in a propagation step. And so we really need to figure out which step is slow. Let's write the propagation steps down again. Step 1, okay. Step 1 is our halogen radical in the propagation step. A halogen radical attacks, let's say, methane again. Okay. And this halogen radical abstracts an H, becomes HX, and gives us methyl radical. The methyl radical now attacks my dihalogen, producing methyl X and X dot. Again, we call this step 2 of a propagation steps. And overall, the methyl dots and X dots cancel, and I have CH4 plus X2 going to CH3X plus HX. All right. How can we determine which step of these two steps is the slow step? See, once we know which step is the slow step, we can look at it to determine the relative rates. Use it to try to explain the relative rates of reaction that are observed for different types of molecules. Once you know what is a slow step, the rate determining step, you can come to a better understanding. You see what I mean in a moment. So, what are the chemical difference between step 1 and step 2 that we can use to our advantage that will allow us to sort out which step is the slow step? Well, in step 1, X dot is pulling off an H. In step 2, the methyl is pulling off an X. There's no H being pulled off. So one major difference between step 1 and step 2 is step 1 involves hydrogen abstraction. Okay, I can handle that. Step 2 involves no hydrogen abstraction. These two facts are crucial to understanding how we can nail down what step is a slow step. By using something we learned in the E2 and E1 reaction mechanisms. And that is the kinetic isotope effect. The kinetic isotope effect. Do you recall what the kinetic isotope effect? The kinetic isotope effect is typically used with hydrogen because when you go from hydrogen to deuterium, you're adding a neutron. Hydrogen just has a proton in the nucleus, deuterium has a neutron, and that doubles the mass. Breaking a bond with an atom that has double the mass requires more energy. That is, a deuterium carbon bond has a higher bond dissociation energy. So, if we see a kinetic isotope effect, by going from hydrogen to deuterium, we see a slowdown in reaction when this deuterium's on. Now, step 1 would be affected by changing deuteriums because in step 1, you're pulling off the H, hydrogen abstraction. So going from H to deuterium, if step 1 is our slow step, we'll see a slowdown. So we'll see a kinetic isotope effect when we go to deuterium. However, if step 2 was a slow step, because there's no hydrogen abstraction involved in it, using hydrogen or deuterium, that was a slow step, there would be no change in rate. We'd see no kinetic isotope effect. So kinetic isotope effect is a slowdown, you see, because of going from hydrogen to deuterium. If there's no change, there's no kinetic isotope effect. Why would there be no kinetic isotope effect in step 2? Because step 2 doesn't pull off hydrogen. So all we have to do is time the reaction for methane and then replace methane with deuteromethanes. Time the reaction again. Does the reaction slow down? The answer is, in fact, yes. The reaction slows down. That means step 1 is our slow step. Step 1 is our slow step. Okay. Now, what can we do to explain the relative rates? Changes in speed are controlled by the slow step. Changes in reaction rate are controlled by the slow step. That is, we only have to look at step 1 now. Okay. In terms of relative rates for step 1, allylic and benzylic react the fastest. Allylic and benzylic react the fastest. Why? Well, if I draw an allylic radical, I can see something that happens that is very reminiscent of what we covered when we looked at allylics and carbocations. Allylic radicals and benzylic radicals are resonance stabilized. And resonance stabilization lowers the energy. And you, if you're saying, wait a second, these radicals are intermediates and not transition states, and transition states affect rates. If you're thinking that, you're absolutely right, and we're going to have to take a look at the transition state. We will. But allylic and benzylic radicals are resonance stabilized, and because of that, they tend to react the fastest. They're also the most stable radicals. So this trend I'm giving you is rate of reaction in the first step, but it's also the stability. Radical stability. Next, tertiary radicals. Now, are more stable than secondary. They also react faster. Now, this raises an interesting question. You might say, wait a second, I can understand why a carbocation, tertiary carbocation is more stable because we have inductive electron donation, we have hyperconjugation, we have steric assistance. It's very difficult to understand why tertiary would be more stable than secondary for radicals. Why would a neutral be stabilized by inductive electron donation? Well, you're probably right there. Inductive electron donation and hyperconjugation effects may play a smaller role than they do in carbocation stabilization. Steric assistance would be the same. If you remember, steric assistance was the tendency for the atom to go from bond angles 109.5 when it's sp cubed to bond angles 120 when it's sp squared. 120 is further apart, and so you're getting bulky groups further apart. So that might play a role. Well, in actual fact, you'd be right when you think about that, because if I was doing, let's put a positive charge for carbocations and a dot for radicals. If tertiary was here and secondary was here in carbocations, that is the energy difference here. Secondary was that much less stable than tertiary. Comparing similar radicals give you a smaller energy gap. And that is the energy difference between tertiary and secondary is smaller than what you get in carbocations. That is, in a radical, a tertiary, yes, it's more stable than a secondary, but that more stable is not as big as it is in carbocations. So the stability difference is smaller. Okay, so allylic and benzylic is more stable than tertiary, is more stable than secondary, is more stable than primary, who's more stable than methyl. This also holds true for the rate. Allylic and benzylic reacts fastest. So let's write that down again at the top. Here, allylic, benzylic react faster than tertiary, who react faster than secondary, who react faster than primary, who react faster than methyl. And while the trend for carbocations stability, carbocation stability, tertiary was more stable than secondary, was more stable than primary. If you did the same thing for radicals, and you put tertiary down here, secondaries, the energy difference between them is smaller. Now this leads to one thing that often allows students to breathe a sigh of relief. One of the things we had to worry about in carbocations was rearrangement, 1-2 shifting. And the rule was you always shifted to get a more stable carbocation. In radicals, the energy difference between the radicals is not large enough to allow for 1-2 shifting. So in radicals, 1-2 shifting isn't as important as it is in carbocations. Often when you say this to students, they breathe a sigh of relief. So back to so we don't have to worry about the 1-2 shifting that we saw in carbocations. Having said that, let's get back to our trend and raise the issue of, okay, the rate parallels stability, but we are talking about intermediates. Why can we discuss the radical intermediate in terms of relative rates? And the answer to that, of course, is the same as carbocation. You only can talk about the intermediate, the radical. Okay, so this trend is the rate of the reaction. It is also radical stability, same trend. But radicals are intermediates, so they're not transition states. Let's look at the first step of the propagation and this time draw a transition state for it. Okay, so I'm going to draw a transition state. So we've got Br dot. We're going to react it with HC. And let's make our C chiral. So I'm going to put an ethyl here. I'm going to put a methyl here. And I'll put a propyl here. So we'll have a tertiary H. That's chiral. What's interesting is this is a slow step. I'll draw the transition state now. So here's my square bracket. The Br starts to form a bond to hydrogen. The hydrogen starts to break its bond with carbon. As this happens, the groups start to flatten out, going trigonal planar. The carbon is rehybridizing to sp squared. Although my artistry probably doesn't show it very well. Okay. Now, as in all transition states, I draw my double dagger. And I have to show which bonds are forming, which bonds breaking. So this bond is forming. This bond is breaking. And here's the important point. Notice what's happening in the transition state. The bromine is losing its lone electron. As that bond forms, it's losing its radical character. As this bond breaks, this carbon's starting to get radical character. What will happen next, after the transition state, of course, is you get HBr. And you get your trigonal planar radical. Now, this just circled in red. Remember, this trend up above is made using the intermediate radical. It is made using this guy. Okay? But rates is controlled not by intermediates that exist in the valleys in the potential energy diagram, but rate is controlled by the transition state. We've looked at this. We've talked about this. So why can I use radical stability to explain rate? Well, the truth is you can't. You only can use radical stability, and we said this in carbocation chemistry, is if the transition state has radical character. If you look at the radical here, the transition state as I've drawn it here, you see there's a delta dot on carbon, which suggests there's some radical character on carbon. As long as that's true, this rate will hold true. If this rate holds true, it'll be because the transition state has radical character. How significant this is depends on how much radical character the transition state has. And this leads to our next dilemma. You see, not all is right in free radical halogenation. What do I mean? Well, take a look at the following reaction. Suppose I give you propane. And in propane, I'm going to do monohalogenation. And I compare chlorination to bromination. That is, in the upper one, I do Cl2 and H nu. The bottom one's Br2. Well, there are two possible monohalogens I can make. I can stick the bromine on the end, which would be a primary, or I could stick it on the middle carbon. So, here's the secondary bromo, and here is the primary bromo. And if I look at percent composition, 98% of the product is the secondary. Only 2% is the primary. And indeed, that makes sense. Why? Secondary radicals are more stable. The major product is the secondary radical, which will make the isopropyl bromide. We've just talked about that. So this is sound. In chlorination, we can make the same products, CH3, CH, CH3. We get the isopropyl chloride plus the propyl chloride. In this case, we only get 55% secondary and 45% the primary. What is going on now? We have identical reactions, other than just shifting the halogen. They're both going by the free radical mechanism. One seems to follow the trend on radical stability, and the other doesn't. It's almost 50-50. We often use the term selective. That is, bromination selects for the secondary only. Bromination selective. Whereas chlorine gives both. It's not selective. It doesn't select. Why is chlorine not selective and bromine selective? Clearly, this is something that we must be able to explain in the light of the information we've already given about the reaction mechanism. And we'll do that in our next Scribblecast. I'm Dr. Brian Lloyd. This is my Scribblecast.